Okay, Taylor and Maclaurin series. In this video, you're going to be introduced to the Taylor and Maclaurin series. Now this section, section 10 in chapter 11, it's a really long section. I think it's the longest in the entire book, and the concepts are pretty difficult as well. I wouldn't say quite as difficult as like if you're learning integration for the first time, what is integration and how to integrate. That's probably the toughest in the entire calculus book. So not quite as hard as that. However, I think one of the additional factors that makes this section tough is that it comes at the end of Calculus 2. You've put all this effort to go through integration, parametric equations, and polar coordinates. Then you come to infinite sequences and series. This is a really long chapter. You go through the entire chapter, and then at the very end of that comes the Taylor and Maclaurin series section. You're worn out, and you get to this section. I think that's what makes it difficult. That's what made it difficult for me. Okay, but again, it is difficult, but it's not that bad. It's not as tough as integration. Okay, so in this video, I'm going to introduce you to the Taylor and Maclaurin series, and then we're also going to talk about the idea of how you have to prove that a function is equal to its Taylor series or Maclaurin series before you can like officially set them equal. You'll see what I mean later in the video. Okay, so again, let's recap what we're doing here. In the opening 7 sections of this chapter, we were introduced to sequences and series, and then for like 5 sections we're all about performing tests on series to see if they're convergent or divergent. Okay, now these last 4 sections are, the goal of these last 4 sections is that we want to be able to represent a function as a series. So you have a function, in any function, e to the x, sine of x, cosine of x, whatever, and you want to be able to say like, e to the x is equal to, and then write a series for it, an infinite series. That's the goal, okay? And so to do this, we're going to do this with power series. We're going to strictly focus on power series. For the goal of representing a function of a series, we're going to do this with a power series. So the rest of this chapter, 11.8, 9, 10, 11, is all about we're working with power series. So in section 11.8, we learned what a power series was. And then in the previous section, we just kind of got some practice with the mechanics of representing a function as a power series, where we used a simple power series as a base function, the geometric series with starting term 1. And from that, we kind of built some power series representations of functions. Okay, but now in this section, we're going to think about, in general, how can we represent a function as a power series? We don't want to be limited by, having to just always start from 1 over 1 minus x is equal to the sum from n is equal to 0 to infinity of x to the n, right? The geometric series with first term 1, we don't want to be limited to just having to branch out from this. How can we think about, in general, representing any function as a power series? And that's what the Taylor and Maclaurin series are all about. Okay, so it says, in the preceding section, we were able to find power series representations for a certain restricted class of functions. Here we investigate more general problems. Which functions have power series representations, and how can we find such representations? Okay, so how can we think about representing any general function as a power series? Again, we're talking about a power series. Remember, this is a power series. Centered at A. How can we think about, in general, for representing any function in general as a power series form like this? So what they do is they say, okay, well, the idea is you have a function f of x, and that's equal to, and then they write out the power series. So they write this out. You have a c sub 0, just a constant with no x's, and then each of these constants is dependent on n. It's not a geometric series. These coefficients can change. Okay, it's centered at a, and then with the absolute value of x minus a is less than r, so the power series is going to have a radius of convergence. So we're going to have the idea is we have a function, any general function, is we want to set that equal to a power series, and it has a certain domain where it converges. That's what we're trying to think about in general. Okay, So it says, let's try to determine what the coefficients must be for this to be true, each coefficient. So to begin, it says, notice that if we put x is equal to a in equation 1, the center point, then all terms after the first term are 0, and we get f of a is equal to 0. So yeah, if you plug in a here, what happens? Every single term but the constant term with no x on it goes to 0. So you plug in a to the function, and that's going to be equal to the c sub 0 constant. So we've solved for the c sub 0 constant. This is, again, this is general for any function. We're working in complete general here. So if you want to solve for the first constant, you plug in a to the function. Okay? Now, we know how to differentiate a power series. So if we differentiate the power series, we talked about in the previous section how you can think about that in terms of differentiating the actual summation, or you can think about it term by term. And that's what they do here. They write it out term by term. The c sub 0 goes away, and then the c sub 1 term, the x minus a, gets eliminated. You're left with just c sub 1. And then every successive term, you still have an x variable, but the power reduces by 1. But the radius of convergence, we know, doesn't change. Not the interval of convergence, the radius of convergence doesn't change. Like, this is still valid. Okay? Plug in x is equal to a here, you get a similar result to what happened with the original function. Everything goes away but this c sub 1 term. Now notice though, this c sub 1 is the exact same as these two are exactly the same. Right? The c sub 1 and the original function, these two are exactly the same. So we've solved for what c sub 1 must be. This c sub 1, this is what we're trying to solve, this function here. We're trying to get the coefficients. If we know what a is going to be, we pick a. So we don't have to solve for a. We pick a. X is a variable. So if we can solve for the coefficients, then we've solved this question we're trying to answer. So you can see that the first two coefficients are solved for. All right. So now you do another differentiation, and you get that. What happens here is, so you differentiate again, and this x minus a goes away, and you have 2 c sub 2. So it's a little bit different. Here, we didn't have any kind of coefficient in front of the c sub 0 and c sub 1, but now we've got this coefficient in front of the c sub 2, but still, we found that f double prime of a, the center point, is equal to 2 c sub 2. And again, these are the same coefficients. Okay, differentiate again. This goes away, and you're left with this constant term with no x on it. So you set f triple prime of a, everything goes away, but the constant term, this 2 times 3, so f triple prime of a is 2 times 3 times c sub 3. Okay, so again, this c sub 3, and they write this as 3 factorial, right? 3 times 2. You can say that's 3 factorial, right? 3 factorial is 3 times 2 times 1. But again, this is c sub 3. Okay, now if you keep doing this, what you figure out is that if you take the nth derivative of the original function and then you plug in a, all the terms get eliminated. And in general, the idea is you get that's equal to n factorial times c sub n. Okay, now it's kind of confusing because the first 2 terms the coefficients were 1. Well, the way this works, remember that the definition of factorial, 0 factorial is 1 and 1 factorial is 1. So that's how it works out to where these first 2 are 1. The coefficients are 1. So this is 0 factorial, then 1 factorial, then 2 factorial, then 3 factorial, etc. So if we divide both sides by n factorial, we've solved for c sub n. The nth derivative evaluated at the center point over n factorial, that's every single coefficient. All right, so that's it. Once we've solved for the coefficients here, we've solved the answer to the question, right? We don't need to solve for a. We pick a. X is just a variable, so there it is. Okay, so now if we come here, this theorem 5 sums all of this up into like a theorem package. It sums everything up. It says if a function f, that's like f of x, has a power series representation at the center point A, that is, if, so f of x is equal to this power series with this radius of convergence, then the coefficients are going to be given by this formula here. Okay, now here's where some confusing, tricky points start to come in that make this section challenging. If you notice this theorem, it says if a function has a power series expansion at A. So if it does, what does that mean, if? Well, okay, what we're going to see is that, yes, this is a really, really good math work here. And what this is going to show is that, like, if you can take a function and write it as a power series this way, so, a function has to be differentiated an unlimited number of times, for example. But so if you can write a function this way, as a power series this way, most of the time you can just set that function equal to the corresponding power series that you wrote for it. But it's not 100% fact that that's true every time. You have to, this unfortunately is not an official proof that a function is equal to a power series with coefficients given by this c sub n here. Now, to me, it seems like it's a proof. It seems pretty rock solid to me. But I'm not a mathematician, but my guess is that it comes from the, series can have odd behavior, and so you can't use this as an official proof. But most of the time, most functions, if you can write a power series representation for that function, so if that function has an infinite number of derivatives, for example, etc., most of the time that function is going to be equal to that power series. But it's not 100% every single time. And so because of that, one of the things we're going to need to learn in this section is how can you, once you have a power series formula for a function, how can you state definitively that, okay, this function is equal to this power series? All right, so if we come back to the theorem here, one thing that it's going to be important for you to understand, so you don't get confused as we keep going here, if you notice there was kind of two criteria I was mentioning about what a function needs to kind of pass in order to be able to say, okay, like this, like this function is equal to its power series. There was two criteria. The first criteria was that you have to be able to it has to be a function to where you can actually get its coefficients like this for any n value, meaning, the function needs to have like an unlimited number of derivatives. And not only that, but it needs to be, you can't have a situation where for some of those coefficients, maybe you can get its derivative, but when you plug in the x, for some situations, you're dividing by 0, so the c sub n doesn't exist or something like that. That can't happen. It needs to be going from n to infinity. You've got to evaluate every single one of the coefficients. You can take the derivative, plug in the center point, and you get like a real number. There's no domain issues or anything. That's the first criteria. You have to be able to write a power series representation of a function. So the notation I'm going to use to illustrate that is this. So you start with a function, okay? You start with a function. The first criteria is that not that the function is equal to its power series representation. It's, you think about it, you have to be able to make a power series representation for the function. Right? So these aren't equal. You haven't proven that these are equal, but you can write its power series representation. That's what this, if you can do f of x with this arrow and put the power series summation, you're saying that, okay, it's past the criteria where it has sufficient unlimited derivatives and there's no domain issues. You can write its power series representation. That's the first criteria that needs to be passed. Okay. Now, what I was just talking about was that you would think that, this proof on the first page here was enough to say that once you can do this, well, then you could just go ahead and set these equal. Right? You would think. But unfortunately, it's in most cases, yes, that will be true. But it's not 100% official proof. So we're going to have to talk about in this section how you can prove officially that you can, once you have this, what do you need to do to prove officially that you can then state this? Okay, now with that, let's reread this theorem again. What is this theorem saying? It's saying, so if f has a power series representation expansion at A, that is if you can set f of x equal to a power series, right? That's all they've done here. They said f of x is equal to, and this is the general form of a power series. If that's the case, if it is the case that a function is equal to a power series, if it's the case that a function is equal to a power series, then the coefficients are going to be this. There's no other way. There's no other, that's a fact. There's no other derivation you can come up with to represent a function a different way as a power series. If a function is, if you have any function that's equal to a power series, then the coefficients are going to be this, 100% every time. Okay? That's what this theorem is stating. All right. So next, what do they do next? Next, they take the C sub n here and they plug it in to the power series formula. Okay? So you get, there's the C sub n. Okay? Then they write out some terms here. You can see you've got 0 factorial, x minus a to the 0. So this is just f of a. F to the 0, like the nth derivative, that just means there's no derivative taken. So this is just f of a, and then f prime of a over 1 factorial x minus a to the first, f prime of, or f double prime of a, evaluated at a, over 2 factorial x minus a squared, etc. Okay, this here is called this is the Taylor series. And the Maclaurin series is just what they call a Taylor series that with a is equal to 0. So a Maclaurin series is a Taylor series. It's just a Taylor series centered at 0. Every Maclaurin series is a Taylor series, but not every Taylor series is a Maclaurin series. Taylor series is the general, is kind of the general term for this. Okay, and you can see that the Maclaurin series is nice because each of the x minus a terms just becomes like x to the 1, x to the 2, x to the 3, and then the derivatives you're evaluating, you're taking the derivative and then you're plugging in 0, which is nice. Okay, it says, note, we have shown that if a function can be represented as a power series about a, then the function is equal to the sum of its Taylor series. But there exist functions that are not equal to the sum of their Taylor series. An example of such a function is given in exercise 84. Okay, so yeah, this terminology gets confusing. And it gets confusing because you can have, okay, you have a function, right? That's one term you can think about. You have a function, like e to the x or sine of x. It's just a function that we're potentially wanting to represent as a power series, okay? That's a term we'll be throwing around, the function, okay? Then you've got, that function can have it might or might not have a Taylor series or Maclaurin series. It depends on if it has an infinite number of derivatives and there's no domain issues. But you can have a function and you could say that function doesn't have a Maclaurin series or Taylor series. Or you can say that function has a Maclaurin series or Taylor series, and they refer to that as the Taylor series of that function. That's, if we come back here, that's kind of this here. This function has a Maclaurin series. This is its Maclaurin series. But I'm saying it that way because we haven't said that just because it has a Maclaurin series or a Taylor series doesn't mean it's equal to that Taylor series or Maclaurin series. A function, there are examples where a function has a Maclaurin series or a Taylor series, but it's not equal to it. And that's what they're saying here. There exist functions that are not equal to the sum of their Taylor series. Okay, but notice this is Theorem 5. It says if f can be represented as a power series about a, it's going to be the Taylor series. There's no other. If a function has the ability to be represented as a power series, we're talking about just about power series, then it's going to be its Taylor series representation, 100%. There's no other kind of derivation you can come up with for some other type of power series that's not the Taylor or Maclaurin series. So if a function is able to be represented as a power series, if a function is able to be set equal to a power series, then it's going to be the Taylor or Maclaurin series, wherever you're centered. Okay. So now let's do an example here. It says find the Maclaurin series. This is the simplest example we can start with. The Maclaurin series, so centered about 0, of the function of e to the x. and we're also going to get the radius of convergence. Okay, so what we're doing here is we want to find, if there is one, a Maclaurin series representation of e to the x. That doesn't mean we're proving that it's the e to the x is equal to the Maclaurin series representation. We just want to find its representation if there is one, and the radius of convergence. Okay. Now, whenever you're finding these Taylor or Maclaurin series representations, the general process is what you're going to do, and they don't really do it here because it's so simple, but you're going to write out, so like f of x is equal to e to the x. You can write the function. Then you're going to go ahead and just take derivatives of the function, like as a function of x. So it's e to the x. F double prime of x is e to the x. F triple prime of x is e to the x. And write out enough of those until you can see a pattern. Or you can say that you can identify maybe that there is no pattern. You write out a few of those. This is 3. Okay? That's the first thing you do. Then you draw a line here and you plug in the center point. So there's no need to put like x minus a here. Like if we were doing this centered at 2, let's say, we were doing that like not x minus a, not a is equal to 0, then we were doing a is equal to 2, then I would put, okay, what is f of 2? That's e squared. What is f prime of 2? That's e squared. Right? There's no need to put, for this step, there's no need to put x minus a or anything like that. We're just saying f prime of, or we're just saying f of x and just taking the derivatives of the function of f of x. And then we're plugging in, then we're coming to the other side and plugging in the center point. Well, here it's the center point is 0, which is nice. But you can see, even if it's not 0, it's not so bad. Like we had e squared each time. It's not so bad. But f of 0, e to the 0 is 1. F prime of 0 is 1, etc. And you do that, and so you can see the pattern. You can see the pattern of actual numbers that corresponds to the pattern of function derivatives. But what you can notice, though, is that with the power series representation, you're plugging in the center point. So you're not going to have the actual function itself is going to go away because you're plugging in the function, right? If we come here, it's n is equal to 0 to infinity f of x. So you're saying it's f nth derivative of a over n factorial. That's the coefficient. And then it's just a power series term. This is all about a power series. So you can see here the nth derivative. Yeah, here the nth derivatives, you still got the function. But then once you plug in a value, there's no more function anymore, right? You're getting a number. I mean, if it was centered at 2, we'd have like e squared. But you know, the function, you have f of x here, but in the power series, the function is gone. See? And so if you take a look, so for every derivative, you plug in the center point. Here it's a Maclaurin series. You plug in 0 to the derivative, you get 1. Well, okay, here it is. Here's the power series. You know, you can notice that they're not saying e to the x is equal to. They're not putting that. They're doing that on purpose because we're not proving that this is the case in this example problem. We're just finding the Maclaurin series representation. So yeah, so f to the n, the nth derivative evaluated at 0, this is always going to be 1. A is 1, so it's just x to the n. And then there it is, x to the n, because this is 1 over n factorial. That's it, right? It's weird because like the e to the x has disappeared. But that's how it is with these Maclaurin series, Taylor series. The function like disappears. Okay, so that's the Maclaurin series of e to the x. Even though we haven't proven that they're equal, this still is the Maclaurin series of e to the x. And if e to the x is going to have a power series representation, then it's going to be this, 100%. It's either not going to have a power series representation where it can't be set equal to a power series, or it will, and it will be this and only this. Okay, so they write some terms out, 1 plus x over 1 factorial plus x squared over 2 factorial, etc. Okay, so now, even though e to the x is not we can't set it equal to this. We can still find out what the radius of convergence of this series is. We use the ratio test. So they apply the ratio test, and the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is 0 for all x. So the radius of convergence is any x from negative infinity to infinity. Or, well, I'm not saying that right. The radius of convergence is infinity. That's what r is equal to, but the interval of convergence is negative infinity to infinity. Okay? So now, what are they saying here? Read this carefully. The conclusion we can draw from Theorem 5 was this. This is Theorem 5, is that if e to the x has a power series expansion at 0, and that's another thing that gets confusing. We're just talking about e to the x at 0 here. If we centered e to the x about some other point, then we just have to start all over. So if e to the x has a power series expansion at 0, then it's going to be it's going to be this. If it does, okay? So how can we determine officially whether e to the x does have a power series representation? All right, so to do this, it says, let's investigate the more general question. Under what circumstances is a function equal to the sum of its Taylor series? In other words, if a function has derivatives of all orders, so, the way, to me, what they're saying here is that if a function not only has derivatives of all orders, but there's no domain issue. So I'm writing it this way. If f can be written as, and they're going to start calling it, so instead of writing out the whole power series, you'll put capital T of x, like Taylor series. And remember, this includes McLaurin series, right? So if a function, and also it depends on the center point, right? All of this, you have to kind of start from scratch based on every center point. So if a function can be represented, I should technically put x minus a. If a function can be represented, not equal to, as a Taylor series with no issues, so it has infinite derivatives, etc., then when is it true that this is the case? Okay, so now they switch to the perspective of, it says, as with any convergent series, this means that f of x is going to be equal to the limit of the sequence of partial sums. Okay, so what they're saying here is that they're just redefining this, is all they're doing. If f of x is equal to this, then f of x is also equal to, what's another way we look at an infinite series? We look at an infinite series from the perspective of, you can write it as a partial sum. So you take this and you say that we called it S of n, and then you change from n to I for the sake of the partial sum, and you do this. And then it would be f of I, right? That's the idea with partial sums. And it's nice if you can come up with like an explicit partial sum formula. And then you think about the infinite series as you take the limit as n goes to infinity of this. So all they're doing with here is they're switching to this perspective of, if f of x is equal to this, then it's equal to the limit of the partial sum formula. Okay? And so it says in the case of the Taylor series, the partial sums are, so yeah, there you go. You see, they've got that, they've changed from, it goes I is equal to 0 to n, for the sake of writing it as you could pick an n. Okay, but you can see I didn't have to put x minus a, so it's like capital T with no n of x is the infinite Taylor series, but you could do the partial sum Taylor series like that. And it doesn't have any need to put the center point. Like I don't have to put x minus a, but okay. A new term though here, so they write out some terms of the partial sum of the Taylor series, but then they introduce another term here. You call this is called a Taylor series, the infinite sum. This is called a Taylor polynomial, and it says nth degree Taylor polynomial. So that's what, if you might hear both of those terms. A Taylor polynomial is talking about like it's like the first 10 terms of a Taylor series, Well, you said n is equal to 10. Okay, now I just want to point out that if you're feeling a little confused, it might be because up to this point, we haven't looked at power series from this perspective of partial sums. Like we spent in the first 7 sections, we looked at partial sums a lot. You know, we looked at partial sums of series, and we talked about the estimating the error, the R sub n. With all of that, we never had an x in those. It was always just a straight up a sub n formula. There was no x involved. So this is the first time you're seeing this idea of the partial sum with an x in it. So just note that might be confusing you because you haven't seen that yet. So take note of that, because we are going to. So okay, you understand what the nth partial sum means for the Taylor series. That's the Taylor polynomial. Okay, so here they write out for e to the x. E to the x is Taylor series. They write out here's t sub 1 of x, here's t sub 2, here's t sub 3. You know, this would be, just to point this out, this would be the linear. We learned linear approximations in chapter 3. N is equal to 1 of a Taylor polynomial is the linear approximation. It's just interesting to note that. But okay, so what we're going to do, though, we're going to use this perspective of looking at the infinite Taylor series, Maclaurin series, as a partial sum to prove that a function is equal to its Taylor series. So okay, they state this here. In general, if f of x is equal to the sum of its Taylor series, then you take the limit as n goes to infinity of the t sub n of x, and that's going to be equal to f of x. So they kind of illustrate this here. You have e to the x, and then they draw the curves for like t sub 1, t sub 2, t sub 3. As n goes to infinity, it's going to converge to e to the x. That's the idea. If we can prove that this is the case, then we can obviously prove that f of x is equal to its Taylor series. However, you might be looking at this and thinking, well, man, how are we going to do this? So we need to get the partial sum with the x variable in it, and then take a limit of that, and it's going to be equal to another function of x. That seems really difficult. You're right, it is difficult, and we're not going to do that. But you do agree, though, if we can prove this, then that would be more of an official rock-solid proof that a function is equal to its Taylor series. Okay? So what they say is that, so let's assume that this is true. If we assume that that's true, then what does that mean? We can think about, so with a partial sum, we can think about the R sub n. Okay, now again, you know what R sub n is from the previous sections. We worked a lot with R sub n, but you've never seen an R sub n of x yet. So just note that it might be kind of confusing at first. It depends, right? Depends on the x you pick away from the center, right? If you pick the center point, then there's no error. But you're approximating it away from the center. And so depending on the x you pick is going to change for any given value of n. Depending on the x you pick is going to change the error. Okay, so R sub n of x is, if this is true, then you take the function evaluated at that x and you subtract that from the t sub n at that same x, right? That's the definition of R sub n. Okay, so now they add t sub x to both sides, and yeah, f of x is equal to the t sub n of x plus R sub n of x. All this makes sense. Okay, so R sub n of x is called the remainder of the Taylor series. And so what we're going to do is, if we can show that the limit as n approaches infinity of R sub n of x is equal to 0, now this is potentially easier, right? If we can show this limit seems just would be too hard, but we could show that something is equal to 0 maybe. If we can show that the limit as n approaches infinity of R sub n of x is equal to 0, then, okay, but still, what does that mean? Well, if we can show this, then what that would say is that you can say the limit as n approaches infinity of t sub n of x. This is true here if we're still assuming this is true. But if the limit as n approaches infinity of R sub n of x is 0, then we've proven this. You see? And so this theorem here kind of summarizes all of that. If you have a function and if that function is equal to its Taylor series, then you're going to have this. You're going to have the partial sum, the nth partial sum of the Taylor series plus an r sub n of x. The function is going to be equal to that. That's you're making a statement there. That's true. Okay, and so the t sub n is the nth degree Taylor polynomial, etc. And then, but if you can prove that the limit as n approaches infinity of r sub n of x is equal to 0, and at least over the radius of convergence, right? That's all we're really concerned about. We don't care about anything outside of the radius convergence. Then the function is equal to the sum of its Taylor series on that interval. Okay. Now, but the question is, you might be thinking, well, all right, I mean, that's fine, but how do we get this r sub n of x? That's what we're going to talk about in the next video.